All right, so I'm going to start this, this lecture slowly so that the people who are outside, maybe a bit late, can catch up if they come at all. So the idea is to continue from where we left off, discussing statistical systems. And I just want to remind you, so last time, we solved a what I call a spherical model. Of a ferromagnet. So the spherical means we had our grid. At each site, there's a spin, which I called sigma. The spins themselves take values from -infinity to infinity. But there's a constraint that they all live on a sphere. And we showed that this model, I'm not going to rewrite the Hamiltonian for now, but we showed that the model that we solved last time undergoes ferromagnetic transition, where if you compute m, which is the expectation value of the average of the spins over all the sites, then this has the following behavior. So as a function of t, there's a t critical. And above the critical temperature, the magnetization is exactly 0. And as you lower the temperature, all of a sudden this thing wants to spontaneously magnetize. And the magnetization goes like that. Actually, we maybe I should redraw this picture. We alluded to this last time, but actually there are two branches of these solutions. The positive and negative branch. Free energy has two minima. And actually, to pick one of these branches, you have to bias the system in some direction first, and then take the bias to 0. Otherwise, it's very difficult for the system to figure out which end state you're going to be in, either this branch or this branch. Okay, so that's a system that undergoes a transition from being disordered. Disordered means that at any site there's no preferred direction. The value of the spin varies wildly as you move along the lattice. And then as you lower the temperature, all of a sudden these things want to order themselves and point in the same direction. So this is sometimes what we call disordered to ordered. Transition. Okay, so so that's the typical story that we tell ourselves in order to understand ferromagnets. Now, a glass or a system that behaves like a glass doesn't have such a disordered to ordered transition. The glass transition, like I mentioned, so, for example, the transition where you have a cup of water pointing in various directions. They might be bumping around, moving, flowing. As you take T towards T glass, then this thing doesn't order, and it just remains the same, just no longer flows. So the dipoles of the water don't arrange themselves in any order. If you had if you had ice, this would form a regular lattice. All of the dipoles of the water would point in the same directions, and you would say the system is ordered. So we want to model this kind of transition. This should be T glass. We want to model this kind of transition, but sticking with a set of spins on a lattice, like so, like the way that we modeled the ferromagnetic transition. Okay, so we're gonna try to change the Hamiltonian that we studied last time in a simple way, and hope that we can model this kind of a transition. So remember, the transition that we want is one where there's a critical temperature. It's important. So what we want there should be a critical temperature. All right. So above the critical temperature, what should the average magnetization be? See if you're awake. 0. Very good. So above TC, what about below TC? So remember, the magnetization is the average direction of the spin across the lattice. And we want to mimic this glass transition. What would it be here? Still 0. So m's not a good order parameter. So, but this is the expectation. There should be a critical temperature. M will be 0 across the phases, but there should be a way to distinguish between the two phases. That's why we have a critical temperature. So, let's try to build something like that. And let's try to build it from first principles. Let's build it.
Tarek, sorry, one question. In the information that you gave to the model last time and so far, is there any actual information about the dimensions of the system? Because you draw a square lattice, but so far there is no information whether this is bidimensional or...
No.
Okay, they could be anywhere. And since
so the model I wrote last time, H was minus J, sum over all sites.
Exactly.
Sigma I, sigma J. But I can solve this model for nearest neighbors. If you want a reference for that, or you can leave it as... It has the same transition.
Okay, is there a way to put information on the model that tells me how many dimensions?
Yeah. You build it like this, nearest neighbor, and you do it in...
The number of nearest neighbors tell me somehow how many dimensions.
Right. Well, okay.
No, but postpone this. Okay, you can continue. But
I'll explain it quickly. So you can always write your Hamiltonian when there's a two-body interaction like this as the state vector sigma I, Vij, sigma j, right? Sum over I and j. And all the information about the lattice is in this V, and integrating over all the spins will give you something that is like the inverse of V or the determinant of V. And so all of the stuff that depends on the shape of the lattice will be in this matrix here. And you can solve it in terms of this matrix. You can find the eigenvalues of this matrix depending on... That's the trick of solving this model. Yeah. This is not This doesn't describe this.
Okay, okay.
This describes the ferromagnet, and here we want we want something that's like a glass, not a ferromagnet. This is the ferromagnet. Any other questions? Yeah. Yeah, so that what you're describing is what is often called block spin coarse graining. And there's a procedure for doing that. What that gives you is a continuum theory, usually. And that continuum theory will be whatever the Landau theory of this model is. So usually it'll be the lambda phi 4 in whatever dimension that you're considering your lattice. Any other questions? Okay. So let's build a model of a glass. With the same ingredients. So by same ingredients, I mean we're going to work with spins on a lattice. The information about the lattice, we're going to do the same trick where we're going to do some kind of all-to-all interaction so that the details of the shape of the lattice will not be important. Okay, so how do we do that? So let's redraw this lattice. So what is the thing that tells me that below some temperature I should expect the system to want to order in this model that I wrote down? What is the thing that forces this theory to order? Energy minimization, that's one thing, but what detail about this Hamiltonian tells me that the things want to order? Yeah, so indeed, the energy is lowered when things are pointing in the same direction, and all the bonds have the same strength. But now imagine if you start to play with the bonds, right? So say, for example, that you have a bond that's like this, negative, which tells you that this spin and this spin, let me use another color. This spin and this spin. Can you guys see that if I use this color? How about that? You guys got to tell me, I don't know. That's okay? So this spin and those two spins now want to align, right? Negative bond. And let's say I have another negative bond over here. These two spins want to align. And a negative bond over here. Just like before, these two spins want to align. But I actually have a positive bond over here. So this guy is happy. This guy is happy. This guy is happy. This guy is not happy. If you flip this so that this guy's happy, this guy's unhappy. So it's a little bit harder to see what's going to happen to a system like this when the temperature is lowered, right? What is the system going to fall into? Is it going to favor satisfying this bond or satisfying this bond? It's obvious that you can't satisfy all the bonds, right? If you could, then you could easily figure out what the configuration is at low temperatures. But because you can't satisfy all the bonds, we say that such a system is frustrated. A system is frustrated when the lowest energy state has some unsatisfied bonds. So it's just kind of annoying, you know? You can't satisfy everybody. It's frustrating. Okay. And the best bet is that if you want to build a toy model of a glass, it should be a system like that. Because if the system is frustrated, then it's hard to say whether or not at low temperature M will be 0 or not. So we want to build a system that has frustration. So let me write down the Hamiltonian that we will consider now. Minus sign again. So you'll see that there's two differences between the model that I wrote down before. The model that I wrote down before coupled only 2 spins together, so it had a 2-body interaction. And this model couples p spins together. And we're going to take p greater than or equal to 2. So for p equals 2, you have a model kind of like that. But now the couplings are allowed to vary across the system. Pick any p spins, and the couplings can vary. It's not going to be the same. And what else do we need to have frustration based off of this picture? Something about the sign of these J's. Now say it out loud. You don't want to say it out loud? Well, the YouTube audience is going to have to wait. Somebody has to say it out loud. Yeah. So these J's don't have a set sign. So J's can be real numbers, not positive. Okay. And if I write down the partition function of this model, so the partition function will be the sum, again, over all configurations. E to the minus beta h. This z will be a function of these couplings j and beta. So it'll depend on these couplings. So you have some lattice of n spins. You have n choose p couplings. So it'll depend on combinatoric number of data, which is the number of couplings. And obviously, this model is not nearly as solvable as the one I wrote before. It's kind of hard to write down for arbitrary couplings what the partition function of this model is. So, oh, and we're going to also have this spherical constraint, just like before.
Tarek, small question. In 1D, you can, well, for 1D in your neighbors, you can solve this for any j in any different site. Do you see there whatever you're going to?
In 1D, what do you mean by 1D?
Just a line of spins.
Nearest neighbors.
Yeah. You can solve it for.
But that's p equals 2.
Yes.
Yeah, you can solve that.
So in that case, do you see anything where you're going to?
There's, yeah, that's a good question. We will see that the system, so we have spin glass physics. for p greater than or equal to 3. There's no free lunch. Okay, so, yes.
So we like to understand this, or we have some theories to understand this. Is there some notion of something similar happening here? Like, so at the critical point, if I look at this Hamiltonian, do I have a funny description in terms of? Or do we know? Is this something that people know, or it's?
Well, like I mentioned before, here our understanding of critical temperature and phase transitions has to do with the fact that you have a diverging susceptibility or correlation length. And that tells you that the theory of the phase transition should be a conformal theory or scale invariant theory. Here, we're not going to see this kind of divergence, so it makes it a little bit less clear what the theory of the transition is. Configurations of the spins. You integrate over all the values the spins can take. That's the partition function. Any other questions? Okay. So this, just by nomenclature, is called the p-spin spherical model. P because you couple p spins at a time. Spherical because the spins live on some large dimensional sphere. And it's this is the model that we're going to be studying over the next few days. Okay, so like I was saying, these j's, having z as a function of j, we're not going to be able to solve that generally. So we will solve this model on average. So what do I mean by on average? So solving this model on average means that we're not going to fuss ourselves too much with what the couplings are. We're just going to assume that the couplings are sampled from some distribution. And the distribution we're going to choose will be Gaussian. It doesn't really matter what the distribution is, but the important thing are its moments. So I'm just going to write down. So this is a probability distribution over the couplings J. It's Gaussian, so you can sample these J's. It'll be either positive or negative. And the mean of the distribution is 0, which is what we want. Doesn't favor plus or minus in any way. And the variance is set by j squared over n to the p minus 1. It's roughly 1 over n to the p minus 1. So at large n, these couplings are not too big. They're pretty close to each other. And we picked this scaling with n because it's going to allow us to solve this model by saddle point later. We're going to have n out front somewhere. But But suffice to say that we're not going to be able to solve this for any specific set of j's. What we're going to do is we're going to have to just disorder average. So these j's are called the disorder. The name is, I guess, self-explanatory. It's disorder because it makes sure that the ground state of the system isn't some ordered thing, and we're gonna average over the disorder. But now we need to answer the question: what do we disorder? So while I erase, are there any questions? All right, I'm going to present two options. So option one. So we want to compute our partition function as a function of the couplings and the temperature. So remember, that's the sum over configs, e to the minus beta h. And then what we do is we average, so we compute z bar. So that's the integral over all the j's. And then from that, I compute an averaged free energy. So that's option one. Option two is first, I solve my theory. Then I compute the free energy. Then I average. So which one do we do? Any guesses? Which one do you think is easier? Option one, option one. Anybody, raise your hands if you think option one is easier. Okay, raise your hands if you think option two is easier. Okay, so the option ones are right. Option one is much easier than option two. So option one, let's look at this. So this is the Hamiltonian. I have j, e to the minus beta j. It's linear in j. If I disorder average z, I just do a Gaussian integral over j, and then I'll get a new effective Hamiltonian, and then I can try to solve that and then take its log. This one, I have to take the disorder average of the log of something that depends on j. Much harder. We don't, and we don't know what the dependence on j is. Definitely not linear. It's going to be some complicated function. So option two is harder, so this is easier. And this is harder. All right, now do you think that the creator of this world is cruel or kind? Cruel. Yeah, very good. Yeah, so option 2 is harder and the one we need. And correct. Okay, so I don't expect anybody to be able to guess why you're supposed to do 2 instead of 1, but let me give you an intuitive reason. So, yeah, I don't know how intuitive this is going to be. The idea is that this kind of average is averaging over the system that you're interested in. You're averaging over the couplings that couple your sites together. But Z, the partition function, isn't a thermodynamic function. It's something that you use to compute a thermodynamic function, but really the thermodynamics are derived from the free energy. The free energy is the object that you minimize in order to understand the physics of the system. And it's very clear that the average of the free energy and the log of the average of the partition function give you wildly different things. But really, it's the free energy that is the thermodynamic object. And so the free energy is the thing that you would naturally think should be the thing that you would like to compute on average, because it's the thing that you derive the thermodynamics from. So we're going to want to compute this, the integral over the disorder of the log of Z. And now I'm going to teach you a trick for how to do that. It's very unintuitive, so we're going to spend some time on that. But I hope the setup is clear. We're studying again, just like before, kind of disordered ferromagnet. And okay, we had to introduce these frustrated bonds. Frustrated bonds make the system harder to compute. So what we're going to do is we're going to compute things on average, but then because we want to compute the free energy, we haven't made our lives simpler. Okay, so we're gonna perform a set of tricks in order to start making this problem tractable. Because as it stands, this problem is completely intractable. Right? You have to do the integral over the spins. It's definitely not Gaussian integrals because for arbitrary p, you have p-body interaction. You have to compute this configurational sum, take its log, and then compute the average over the log. It's pretty complicated. It's a wonder that anybody ever solved this problem. Okay. So trick 1. We're going to use the following identity. We're going to use the fact that log of x can be written as the limit as n goes to 0 of d by dn x to the n. Have you guys ever seen that before? Yeah? No, it's easy to derive. So let's derive it. X to the n is the same as e to the n log x. I take a derivative with respect to n. So I get log x e to the n log x. I take n to 0, I get log x. Okay? There's no magic. Okay, that was an aside. Okay, so it requires that n be a continuous number. so that we can take a derivative with respect to it and then take a limit. But now we will not take n to be a continuous number. We'll take n to be an integer. So we're going to compute z to the n. Z to the n is, we're going to define it as follows. It's e to the minus beta h, and then h is sum over I1 less than IP, j I1 IP. And then now I'm going to add another index. A equals 1 to little n, sigma IA, 1 sigma IPA. So all I've done is that I've written z to the power n in a kind of stupid way that's only valid for n being an integer, which is that I replicate my system n times, and then I just compute the partition function to the power n. It's just n replicas. And yeah, so I1 to IP are in 1 to n, and A is from 1 to little n. Okay? So of course, this thing is z to the n only for when n is an integer, right? Clearly, this doesn't hold for any continuous n. It's just n is 1 or 2 or 3 or 4. And what we're going to do is we're going to compute z bar to the n. So we're going to disorder average this guy. And then we're going to get f bar by taking lim as n goes to 0 of minus 1 over beta d by dn of z to the n bar. Yeah. Sorry about that. Okay, so this step is very iffy. How am I supposed to take a derivative with respect to little n when little n is an integer? And we're going to argue for a trick for doing that, but we'll take it slow. But what we're going to do is we're going to replicate the system n times, and then disorder average this replicated system. And then at the end, we're going to take a derivative with respect to n to derive the thermodynamic free energy. Okay? And you should be very skeptical. You should be very skeptical that this should work. And we'll see. We'll build up slowly why this works. It's a big surprise. It took many years for people to become convinced by this kind of reasoning. So if you're skeptical that this should work or give you any extra insights, you should feel confident that that intuition is correct. Shouldn't be able to get something for free out of this.
Sorry, is your claim that that computation will yield the option 2 result?
Mm-hmm.
Very good.
Yes. It's weird. Any other questions? No? Shall I move on? I'll show you how to do these calculations. Yeah.
How is this any worse than doing dimensional regularization? in which we also have an integral over an integer dimension, and we make it continuous?
I wouldn't say it's any worse. It's maybe just as iffy. Well, maybe this is more iffy. Maybe this is more iffy. I don't know.
Okay, thank you.
You'll see. You'll see. I don't want to spoil the surprise. You'll see. Some weird stuff arises by doing this. Any other questions? By the way, since you guys are all holographers, how many of you have seen the island formula in your studies of high energy physics? Some of you? Yeah, the island formula arises by some trickery like this. The gravitational path integral computes for you an average over couplings, roughly speaking, and then you get new interesting results when you take the number of coupling or the number of replicas to 0. So this kind of trickery has been used in high energy theory very recently. Any other questions? Okay. So we want to compute z bar to the n. So we want to sum over configurations and disorder average that theory. This is much easier to compute than this guy, which is solving the model for n equals 1, taking its log. We can't do that. There's no way we'll ever be able to do that. You can try at home if you want, but it's very difficult. Okay, so just as before, let's compute. So what's z bar to the n? Well, this is the integral over all of the couplings, p of j, times the integral, minus infinity to infinity, of d sigma I1 minus infinity to infinity, d sigma I n, or sorry, d sigma n, d sigma 1. I need to insert the delta function that fixes my constraint. And then I just have okay? So this is exactly what we did before. Before we didn't have a disorder average, so we didn't integrate over the couplings, but we did have this constraint. And before, all we had were a bunch of Gaussian integrals, so we could just compute this pretty straightforwardly. But now we don't have a Gaussian integral, so we don't know how to compute this. But everybody agrees with what I wrote down? It's straightforward. I'm just computing e to the minus beta h, and then replicating it n times, and then disorder averaging. And sorry, this should be a, and there should be a product over a here. And there should be an a here. So for each replica, there is a spherical constraint. Okay? So now what do I do? I have a Gaussian integral over the j's, something linear in the j's. So I can just integrate over the j's. It's pretty free. That's the easiest part of the problem. I just can do the Gaussian integral over these j's. So let me do that. So the Gaussian integral over these j's, you complete the square, right? When you complete the square, you're going to have something with replica index A coupled to another something with replica index B, right? Because you're summing over replicas, and you're integrating flat over the j's over all replicas. So what this gives you is an integral. I'm not going to write all of the integration measures. And then you have, I'm going to be explicit with all the factors because they come from that, e to the beta squared, j squared over 4 to the np minus 1, then sum over I1 less than IP, sum over A B equals 1 to n, sigma I1A, sigma IPA times sigma I1B, sigma IPB. And then I can close this parentheses on the other board. Okay, so the indices on the top line. Yeah, so you should think of this product is over A for these integration measures. So for A is 1, you have this integration measure. A is 2, same integration measure. Okay, so what have I done? I had a system, I replicated it n times, I have my disorder, and I integrate over it, and all of a sudden, I coupled the replicas together. And this is the fishy part. The replicas should never be coupled. I mean, you're just replicating the system n times. Shouldn't be any effect to having these systems coupled. But the upshot of this calculation, as we will see, is that at low temperatures, we can capture some physical effect by showing that this coupling between replicas actually has an effect on the physical observable when I take the derivative n to 0. Okay. So I'm going to leave this as an exercise for you to do in the exercise session. If you're paying attention, what exercise are we on? How many have I assigned so far? Yes, very good. This is the 4th exercise. So, exercise 4 is argue that okay, so, and sorry, there should be a p factorial here. that comes from this p factorial. So using this homework exercise that I'm giving you, I can rewrite this. This comes down as okay, so what have I done here from this step to this step? Notice that you can pair up I1A and I1B, and there are p of these pairs. And all I need to do is, using this ordered sum with a p factorial, if I can write it as just n separate sums over I1 and IP, then I can write this as the same sum over I powered to the p. That's all I've done in that step. And now I need to integrate over the sigmas. And this is clearly still not Gaussian. I still don't know how to do it. The only thing that we know how to do in theoretical physics is Gaussian integrals. So we need to figure out how to make this a Gaussian integral. Okay? So that's our next task. Make this a Gaussian integral. Having the little p fixed, it's not super important for the physics so long as it's bigger than 3. But I'm going to keep it unfixed so that we can see that p equals 2 doesn't do the job. You mean if your Hamiltonian was sum of p body and p1 body interactions and p2 body interactions? Yeah, you can do that. It's just more difficult. Doesn't change very much. We want the simplest model. We don't want to necessarily complicate our lives. I mean, we're complicating our lives by trying to find a model for a spin glass. But all right. All right, so just let's back up. What are we doing? We have this thing. We want to compute we want to find a model where the physics is the physics of frustration. At low temperatures, the system is still disordered, but nevertheless, there's some signature and there's something that characterizes this phase. So what we did was we wrote down a Hamiltonian, had disorder, so the ground state wasn't some ordered thing. And now we're just trying to understand the physics of that object. And we had to do a bunch of things in order to make this problem tractable. First of all, we had to integrate over the couplings, because solving it for arbitrary couplings is hard. But we had to do it in a way where we first compute the log of the partition function. Of course, computing the average over the log is hard, so we did this other trick of introducing a bunch of replicas. And then at the end, we're going to take the number of replicas to 0. So it's just a recap of what we've been doing. And the manipulations have led us to this point. We've integrated over the couplings. We still haven't integrated over the spins, so we still don't have the partition function of the replicated system. But we're getting there. So now we need to massage this system even more in order to be able to derive the free energy. Okay? So we clearly can't do the integral over the sigmas yet. It's not a Gaussian integral. We don't know how to do it. So what we're going to do is we're going to introduce a new variable. So we're going to introduce a variable which I'm going to call QAB. So notice that this is a matrix in replica space, but it sums over all the lattice sites. What you can think of this object is that you can think of the spin, sigma A, as a vector that represents the configuration of the system, of replica A. And then I dot it into the configuration of replica B. And what that is measuring is the angle between these two configurations, right? In particular, this is a vector of, so this is the spherical constraint. So these are vectors of size root n. This is a vector of root n. This is a vector of size root n. So if I divide by n, then this is a cosine of some angle. Measures the overlap between the two configurations. So if it's 1, these configurations are very close. If it's pi over 2, configurations are far. If it's minus 1, they're basically the same, just pointing in opposite directions. Okay? So I'm going to introduce this object QAB, which is on shell is 1 over n sigma A dot sigma B disorder averaged. And the notation is this is a thermodynamic average, and this is disorder average. So I'm going to do that by inserting in this integral. So I have this integral over all the spins. I'm also going to insert an integral over QAB, delta of n QAB minus sum over I sigma I A sigma I B. And then there's still these integrals over all the sigmas. Okay? And because I have a delta function now in my path integral, I can replace these sums freely with this Q. Right? So oh, and one more thing, of course, the spherical constraint says that QAA equals say it out loud. I can't see or hear. Somebody say it. I don't know. 1. There you go. Okay. Yes. Let me write down P again. So it was some number out front. I'm not going to rewrite it. So J is the variance of the distribution with some ends pulled out. This is a square. You'll see, now that I've integrated over J, the things only depend on the dimensionless quantity beta J. So you can set J to 1 if you want and just keep track of beta, but really the things only depend on the dimensionless quantity beta J. Okay, so I'm almost there. So I have this delta function here. And remember, I can always write a delta function of x as 1 over 2 pi integral from minus infinity to infinity dz e to the I z x, right? It's the representation of the delta function. So I'm going to do that with this delta function. So z bar to the n, I will write as the integral of dq ab, something I call d lambda ab, and then there's going to be a product over I and a of d sigma I a, and then I have a delta of q a minus 1 and e to the I lambda ab times n qab minus sum over I sigma I a sigma I b, and then the rest of this stuff, which is plus beta squared j squared times n over 4 times qab to the p. Summed over a and b. Are there any questions? So I hope what I did was clear. I wrote my partition function like this. I collected it in terms of some sigma I, sigma I a b. I introduced this new variable q. I introduced it in the path integral. And now I have things in terms of q. There's a nice factor of n out here, so I know that I'll be able to do a saddle point later. And now all I have to do is integrate over the sigmas, and this is Gaussian. Okay? The lambda is what I called z. Maybe I'll write it as the integral over lambda. Okay, so the lambda just enforces this delta function. And now if I integrate over the sigmas, all I do is I get the determinant of I lambda in here. Right?
I'm sorry, Tarek. Could you repeat again? Where did the integration in dqab came from?
I'm just introducing a new variable. So integral over dqab of nqab minus this is 1.
Ah, excellent. Very good. Thanks.
So I've just introduced 1 into the integral. And it's just a trick. I've introduced 1 into the integral, so I'm multiplying the integral by 1, and using that multiplication by 1 very judiciously. Okay? So this is a very long process that I'm massaging this complicated n-replicated object, but we're getting close. Now we can finally integrate out of the spins, and we'll be left with an effective theory of q and lambda. So we have integrated out the lattice completely, and we're just left with we'll be left with a theory in replica space, which is weird. We didn't start with any replicas or anything like that, but integrating over the couplings forced us to have to consider that. Is everybody following, or should I slow down? Should I speed up? It's good? Good pace? Doing all right? Okay. So we just have to integrate over the sigmas now. And this is Gaussian, so just pay attention to that blackboard. So I'm just going to use the fact that the integral over sigma I A e to the minus sigma I A lambda A B, and there's a sneaky I in here, ignore it, sigma I B. So let's fix I, or maybe I'll just write this as J so that I don't confuse with the other I in there. Let's fix J. The integral over J summed over A and B gives the determinant of that matrix. And then doing the product over J will give that determinant to the power n, right, because there are n of these spins. So this gives, if we're being careful, det of the lambda matrix over pi to the minus n over 2. And I'm going to write that as e to the minus n over 2 log det of I lambda over pi. This is the matrix. And then I'm going to use the fact that the log of the determinant is the same as the trace of the log. You guys have seen that identity before, that the log of the determinant is the same as the trace of the log? Right? It just has to do with writing down the eigenvalues of this matrix. The determinant is the product of the eigenvalues. The log of the product is the sum. Okay. Now, if you look over here, I have n over here. I've gotten rid of this. N over here, and an n over there. So everything has an n. And n is big, n is huge. So now I'm not going to do any integrals anymore. I'm just going to do saddle point. Thankfully, I picked my distribution to have n to the p minus 1. Because if I didn't, then I wouldn't have these factors of n. So now I've simplified my problem to a theory of matrices in replica space. Of course, I have to integrate over them. There's a complicated integral because this is q to the p. I don't know how to do that integral. But there's an n out front, so all I have to do is evaluate this on the saddle point equations. Okay? And I'm going to do one last trick. I'm going to get rid of lambda. So now I have trace log of lambda, and lambda multiplies just q. So I can find an equation for lambda in terms of q. And just by varying this action with respect to lambda, so you can do this at home, the variation of the action with respect to lambda gives that lambda AB is equal to 1 over 2i q a b inverse. It's not hard to see that. Take a derivative with respect to lambda AB of the log, you get lambda inverse with the I and a pi. Well, you don't have to worry about the i's because the logs will get rid of them. But then there's you take a derivative with respect to lambda here, you get q. So lambda inverse is equal to q. So lambda is equal to q inverse. And then I'll be left, and then I can write down my effective theory completely. So I'm going to write it down over here. So this leads to an integral over q. Product over a, delta q a minus 1 e to the minus n, and then minus beta squared j squared over 4, sum over a and b, q a b to the p minus a half trace log of q. There's an n out front, so all I have to do is minimize this quantity. And remember, Q is a matrix in replica space. Okay? Q is a matrix in replica space, and it measures the following. It asks, say I have a dirty system, and I replicate it a bunch of times, say little n. And then what I do is I compare the state of my system in replica 1, the thermodynamic state in replica 1, and the thermodynamic state in replica 2, for example. Well, this is a dirty system, right? It's got a bunch of frustrated bonds. As you lower the temperature, it's going to get stuck, right? It's not going to find necessarily the minimum of the energy because there's going to be a bunch of frustrated bonds. So it's not going to know how to explore the phase space appropriately. So what this is doing is this is setting up an experiment where you imagine running the procedure. You have the same dirty system. You have a lot of control, so you can make n copies of your system. And then you just compare the configuration across a bunch of iterations of the system. And you look at whether they find the same state or they're very far. So what do you expect the answer for this matrix to be? It's a very big vector, sigma. It's a dirty system. Do you expect there to be any overlap between any two configurations? No, right? So how many think that the overlap should be 0? How many think that it should be big? How many think there should be a small overlap? How many think that this matrix has no structure at all? Okay. Yeah, mandatory voting in Brazil, please, yeah. I forgot that fact. Okay. Well, before we study this theory, remember, we have to study the equations for Q, the saddle point equations for Q, but we're not done once we solve the saddle point equations for Q. What's the last step that we need to do? Take the log. How do we do that? We did this trick, right? Log is equal to the derivative with respect to n as n goes to 0. So first, we need to study the saddle points and hope that we get some analytic function of the number of replicas that we can trust the analytic continuation of. So we're not out of the woods yet. There's a lot to understand about this effective theory. We're kind of far. But the important thing is that we need to remember that at the very end of the procedure, we have to take n to 0 to get the free energy. Only once we take n to 0 can we say that we're understanding the average thermodynamic properties of this system. Okay? So we're going to study that. This is going to spill over into my next lecture, but that's okay. But let's talk a little bit about this matrix. Is it okay if I erase the distribution now? Okay. So, like I said, this Q, yeah, let me write this down over here. Like I said, this Q, AB, and let's focus on A not equals to B, is the thermodynamic average of two replicas dotted into each other, and then disorder averaged. But if you are replicating the system, then you expect the thermodynamic averages to split. So really, we should write this as and then we take the disorder average. So it's computing the 1-point function in each replica and dotting it into the 1-point function in another replica. Now, of course, if this thing had a ferromagnet behavior, you would expect this below the critical temperature to just give m squared, right? This one with an appropriate factor of n. But so if this thing had a like magnetic behavior, then you could imagine doing this experiment, and of course you would measure that, you know, on average this thing would give plus or minus 1, right? Because either you get the magnet in one direction or the magnet in the other direction. But here we expect the average magnetization of the system to be 0. But the reason that we're getting something for nothing is that we're also doing this disorder average. So this disorder average is not the same as computing separate. This we would expect to be 0, but here we would expect some amount of correlation. If we weren't doing this disorder average, then we would expect this matrix to give 0. But because we're doing the disorder average of the coupled system, we'll expect non-zero. Okay. So what would be your guess? What would be the simplest guess for this matrix QAB? If you were to give an ansatz for it. So obviously, we need QAA to be 1. So if A were equal to B, so for A equals B, we would expect a connected 2-point function. So you might imagine that there could be something non-trivial here, but because of the spherical constraint, we set this to 1. So there's definitely going to be 1s along the diagonal. Okay, so what's your guess? Should on average now, should the overlap between replica 1 and 2 be different than the overlap of replica 1 and 3 or 2 and 3? Should there be any dependence on the replica number? No. That's what you guess? So you guess something in the off diagonal? Something that we would want to solve for, but it'd be the same for everybody? Seems reasonable? Okay. So we're gonna make this guess first. So now exercise 5. Wait, am I at exercise 5? Show that the eigenvalues of this matrix are lambda 1, and the degeneracy is n minus 1. And lambda 2 is 1 plus n minus 1 u with degeneracy 1. What values can you take? Between 0 and 1? Almost. So minus 1 and 1. Okay. So we're going to plug this into here. Desert island style. All right. So this is the sum over A and B, QAB to the P. There are n ones and n times n minus 1 u's. So in the end, z bar to the n will be the integral for u from minus 1 to 1. E to the n beta squared j squared over 4 n ones n times n minus 1 u's. That's this guy. And it's to the p. And then we need to do the trace log, but we have the eigenvalues. So there's n minus 1, 1 minus u's. So plus n minus 1 over 2 log of 1 minus u. Plus 1 log 1/2 log of 1 minus n minus 1 u. Plus. And lo and behold, we have an effective action for u. And I'm going to close my eyes. And I'm going to assume that this is an analytic function in n. So I'll be able to take a derivative and set n to 0. So this kind of matrix, we call it a replica symmetric matrix. So the free energy, the replica symmetric free energy, is I take a derivative of n of log of this, it's minus 1 over 2 beta, beta squared, j squared, over 2, 1 minus u to the p, plus u over 1 minus u, plus log of 1 minus u. And I want to minimize this guy with respect to u. And we'll do that next time.
Okay, questions? Okay.
I don't know if this is a correct question, but it's very general. For the moment, there are nothing out of the equilibrium, right? Or not? Because when you put a temperature fix, it's an equilibrium system, right?
Yeah, so it's a good question. What do I mean by out of equilibrium? So I'm using all of the tricks of equilibrium thermodynamics to study a system that can't reach its equilibrium. Right? It's I have all these frustrated bonds, and yeah. Just let's wait and see what happens. So I agree that it's confusing. Why am I calling this system out of equilibrium? The real answer is that we like to use the tools that we know and love because we're good at interpreting them. We have a lot of experience. But a system like this evades easy analysis. So we need to kind of beef up our abilities, but without going too far. And you'll see what the signatures of the out of equilibriumness is, hopefully.
Okay. I have a question. Here you have this exponential, and you have a minus n, and then you have two minus signs inside. Should I be worried about the plus exponential of something that we integrated?
No, because
I thought it was a typo, but then you wrote a positive exponential
it's
there,
plus,
so
it's plus.
so it's plus.
It's plus. The thing that saves you is that u is only from -1 to 1, so you don't have to like
Very good.
really worry about
Okay,
the
okay.
large excursions.
Very good. Very good. I have a follow-up question, if I let you think for a moment. You have showed me that this integral, since it couples replicas, it's different than option 1. I am sure of that.
Yes.
Is there a way to check that it is option 2? Because perhaps there are more than 2 computations that you can do.
Yeah. You will see.
Thank you.
You will see. There's a surprise waiting in the next lecture.
Okay, so we thank Tarek again.